can start. Other participants will join soon. So good evening to everyone and welcome to this new webinar. The new webinar topics is about the interactions. So I'm going to share my screen. And here we are. So today's webinar's topic is links and interactions between nodes and elements. And basically we will talk about what are the interactions that we use in STKO, how they work in STKO, and how they translate to their OpenSys counterparts. So here is the contents of today's topic. Well, interactions are basically used to connect disjoint geometries. So whenever you have two separate bodies and they should interact with each other, you should use the interactions. Now, interactions are used basically to create two kinds of connections between the two bodies. They can either be kinematic connections or physical connections. What does it mean? Kinematic connection means that there is only a kinematic relationship between the degrees of freedom of the two bodies. Okay, so the most typical ones are equal dov or rigid links. Physical interaction instead means that the two bodies are connected using some kind of constitutive behavior. Okay, so I will first talk about kinematic interactions, starting with the easiest one, so the most common one that you find in OpenSys, which are the equal degree of freedom or the rigid link. There is also the rigid diaphragm, but it is very similar to the rigid link. So what I will say about the rigid link also applies to the rigid diaphragm. Then I will move to something which is slightly more involved, which is the beam to solid coupling and the beam to solid bar slip. They are basically not exactly OpenSys components, but they are STKO's automation that basically can create something that is not already available in OpenSys. And then I will move to physical interactions, and I will give you some examples of distributed springs, so how you can simulate interfaces. Okay. So now the first examples, we will start with kinematic interactions, and I will talk a little bit about equal dovs and rigid links. So now, before going with an example, we need to talk about differences between equal dov and rigid link. Now, the equal dov, as the name says, it is a simple connection between each degree of freedom of a slave node to the respective degree of freedom of the master node. Now, taking a 2D example. Okay, imagine that we are in 2D with 3 degrees of freedom, so 2 translations and 1 rotation. With the equal dov, the displacement and rotation are uncoupled. What does it mean? It means that the displacement of the slave nodes only depends on the respective displacement of the master node, and the same for the rotation, but there is no relationship between displacement and rotation. And in fact, the constraint matrix of the equal dov is said to be the identity. In fact, for example, with an equal dov, I say that the x displacement of the slave node is equal to the x displacement of the master node. Same thing for the y, and same thing for the rotation about the z. So if you look at it in matrix notation, you will see that the constraint matrix is actually an identity matrix. Now, the rigid link is slightly different. Displacement and rotation are actually coupled. And this leads to a constraint matrix, which is not the identity. So for example, with a rigid link, the rotation is equal to the rotation of the slave is equal to the rotation of the master. Okay, but the displacement are not exactly equal to the displacement of the master, but they are equal to the displacement of the master plus or minus, depending on the sign convention, the rotation times the distance of the slave node from the master node. Okay. So this coupling between slave and master leads to a constraint matrix which is not identity. Now, why am I talking about the constraint matrix? You will see that if you use the wrong constraint handler, the rigid link or the rigid diaphragm cannot be used. Okay, so that's why I gave these brief interactions. this brief introduction. Okay, so let's go to STKO, and I will show you a very simple example of what are the differences between equal DOF and rigid links. Okay, so in this basic example, I will not create any element. I will just create a simple model with 4 nodes, and it is sufficient to be in 2D. Just for the sake of simplicity, I want to use a grid size of 1 because it will be easier to read the results. Okay, so what I'm going to do is to go into the geometry. Oh, by the way, this first example is basically here, and of course I will share with you all these examples by tomorrow, and it will be the first one. So 0, 1, basic kinematic constraints. Then we will move to more involved examples. Okay, so basically in this one we are going to create 4 nodes. The first one at 0, then we are going to create another node at y equal to 1, and 2 other nodes like that. Okay, so 4 nodes, and basically here I want to connect the first 2 nodes using an equal DOF and the other 2 using a rigid link, so that I can show you what are the differences. Okay, so we have our geometry are basically 4 nodes. Then we are going to create 2 different interactions. So the first one will be the interaction for the equal DOF. So EDOF interaction. As I said in many other previous webinars, we have 3 kinds of interaction types. Now, most of the times, you just need the node-to-node links. Okay. Now, the node-to-element links is only used in one kind of contact element, which is useful for people in geotechnical engineering. So in this webinar, we'll talk about only the node-to-node links. Okay, so press OK. Whenever you create an interaction, STKO first asks you for the master geometry, and then you need to provide the slave geometry. So in this case, the master geometry will be the first node. So this one will be the master. Then right-click. And then once I click on the right mouse button, STKO asks for the slave geometry. And in this case, the slave will be this one. And right click to complete the creation of the interaction. Okay, so this one has been done. Now I do the same with the other. I create 2 separated interactions because, of course, I want to assign 2 different boundary conditions. So this one will be a rigid link interaction. So same thing, node to node. Okay, so the master will be the base node, right click, and the slave will be the top node, right click. Okay, perfect. So now we have 4 nodes and 2 interactions. We are not going to create any element in this example. We don't need them. I'm just going to create a definition just because I need a linear time series for applying a load. So I call it ramp, and I choose time series linear. Okay. Of course, since we don't have any elements, we don't need physical properties, we don't need element properties, we can go straight to the constraints. So the first thing that I want to do is to keep all the top node free because they are the slaves, and I will impose some kind of displacements at the base nodes. Okay, so applied displacement. So at the bottom, I'm going to create a load. Now, in this case, I want to apply an imposed displacement. So I'm not going to the constraint. I will go to the loads, choose SP, so prescribed value. And here we are in 2D, and I want displacement and rotation. So here, basically, I want to fix the X displacement of the 2 bottom nodes equal to a certain number, to 1, for example, okay? So basically expect the base nodes to move of 1 unit, and they will go here. Then I want to fix the Y displacement to 0. So they are fixed in the vertical displacements. And I want to apply at the same time, so I want to apply both a displacement and a rotation of 0.5 radians, okay? So basically each one of those 2 master nodes will displace of 1 unit and will rotate about the z-axis of 0.5 radians, okay? So this one is the first the first condition. Then we need, of course, to create two conditions to assign to the two interactions. Otherwise, they will not be part of OpenSys. So the first one will be the equal of. The equal of is a constraint. It is a multi-point constraint, so we can find it here. We are in 2D and displacement rotation. And as I said in this matrix form, I want to constrain everything, so all the degrees of freedom. So I simply click all of them, and I choose the first interaction. Perfect. Now I do the same for the other interaction, and this one will be a rigid link. Constraint, multi-point, rigid link. Now in the rigid link, you have a choice. Well, first of all, I need to choose 2D because we are in 2D. Then you can choose between bar or beam. Now, when you choose bar, it is described here, only the translational degree of freedom will be fixed. Now, actually, in this case, we want, so basically it will be like the equal of, but without the third row, okay? So just each displacement will be equal to each one. So in that case, will be exactly equal to an equal of only in displacement. Now, in this case, I want a real rigid link, so I go with beam. Okay? In fact, with beam, I cannot choose anything because with beams, I will constrain everything. And beam, so rigid link with beam will coincide with this constraint here. So before pressing OK, I select this interaction and press OK here. Okay, so we have all the conditions. Now we can go to the analysis steps. Oh, by the way, I need to explain you something. This is the only example I've done without any elements. Now, STKO has an automatic way of assigning the number of dimension and the number of degrees of freedom to the nodes. And basically, it is done based on the elements that are connected to the nodes. Now, in this case, we don't have any elements. So what happens is that STKO doesn't know what to do with these two top nodes. Basically, STKO doesn't know if they are only displacement node or displacement and rotation. So a simple way to force STKO to say, okay, these two nodes, even if there is no element attached to them, I want them to be displacement and rotation. So there is a little trick that I can do. I can simply create a dummy boundary condition, like a fixity, and then I will not apply it to anything. So constraint, single point, fix, and I choose 2D, 3 degree of freedom. Then I do not check anything. So basically, this one will not be part of OpenSys. It is only necessary to say that also these two nodes will be displacement and rotation. But as you can see, this one is useless basically because I'm not fixing anything. Okay, it's just a trick when you don't have any element to say that a node will have a certain number of degrees of freedom. Okay, so now we can go with the analysis steps. As usual, the first one will be the recorder. So I go to recorders, MPCR recorder, and we can call it 01 basic constraints. And I want to show displacement and rotation. This is the only output that I need. Okay. As I said here, we don't have any single point constraint. We have two multi-point constraints. So add boundary conditions, pattern, add pattern on constraint pattern. And we're going to add here the two multi-point constraints. So the equal of and the rigid link. Equal of and rigid link. And then we apply the loads, which are basically the prescribed displacement at the bottom node. So add loads. So we go under pattern, add pattern, load pattern, which is the time series, the first one. And then under SP, we are going to select the imposed displacement at the master nodes. Okay, and now we can go with analysis. Static. I will show you that plane constraint will give us an error. So we'll start with plane constraint, and then I will show you what kind of error we have. Then, of course, this is a linear problem. We don't need Newton. linear. It's fine to have just 10 time steps just because I want to show you the animation. Otherwise, just one time step would be fine. Okay, then first of all, I need to save the model. I'm going to create, basically, I'm going to create another folder like this one. Zero, one. 01 basic constraints. Of course, the first thing to do is to match it. Okay. So now if I switch off the labels, you can see that we have basically 4 nodes and 2 elements. Okay, now we can run the analysis. And here we have a couple of errors. That's fine. So here I have 2 kinds of errors coming from the plain handler. So whenever you see an error like this, which actually here it is a warning, but finally it will lead to an error. It says warning, plain handler. Plain handler cannot handle non-homogeneous constraints. What is a non-homogeneous constraint? A non-homogeneous constraint is a prescribed displacement. So a single point constraint, which is not equal to 0, which is equal to some value. Okay, this one cannot be handled by the plain handler. I've talked about this one also in the previous webinar. And then this fifth error here is the reason why I explained the concept of a constraint matrix being equal to the identity or being different from the identity. Because if you use the plain handler and you use some kind of constraint like the rigid link or the rigid diaphragm, it will say constraint matrix, not identity, ignoring constraint. So basically, it is not applying this kind of constraint. So that's why I explain you what is a constraint matrix, which is not the identity. So basically, you find this kind of constraint matrix with the rigid link and the rigid diaphragm. Okay, so the equal DOF is fine with the plain handler, but the rigid link is not. Okay, so that's why I decided to choose the plain handler. And then, of course, I need to change with any one of the others. Okay, so in this example, I can choose the transformation. Now, with the transformation, everything should be fine. So let me close this one. Okay, our 10 steps. Now, basically, what I expect to see is that both of the master node will displace of 1 unit. Okay. Then the top node will displace of 1 unit as well because it has an equal DOF with the bottom line. While this node, it will be equal to the displacement of the master minus the delta y, which in this case is 1, minus 1, the rotation, which is 0.5. So I expect this one to move of only 0.5. Okay. So I go to the post processor. Let's go into the, and I'm going to open the XS01 output file. Now, obviously, here I don't see anything because I need to show the nodes. Okay. And then let me put this grid size to 1 so you can actually see where they are gone. Okay. So they started from here, as you can see in the animation. Okay. So basically, when you have an equal DOF, they will move exactly in the same way. But in this case, it will move the same way as the master node plus rotations times a distance. Now, in this case, it will be +1 minus 0.5. Okay. And this one, of course, is the X displacement. Let me go to the displacement and not magnitude, but only X. Okay. So this one is equal to 1, this one is equal to 0.5. Instead, if I look at the rotation, they will all be equal. Okay, so everything equal to 0.5. And in fact, it is clear from this constraint. So for the equal DOF, it is equal to the slave, it is equal to the master. And same thing for the rigid link. The only difference is in the computation of the displacement, which for the rigid links are also affected by the rotation. Okay. Okay, so this one basically is a very simple example, just to explain you what is a constraint which is not equal to the identity and what is the kind of error that you can get from OpenSys. Perfect. So now we can move on with the next example. So I save this one and I create a new file. Okay, now moving to the next example, it will be, okay, so as I said here, there is a review of the rules about the constraint handler. I placed them here. They were present also in the previous webinar, just to tell you about this tricky choice about the constraint handlers. Okay, so the next step will be the beam to solid coupling. Now this one is a little bit more involved, but not so much. So basically, what is a beam to solid coupling? First of all, it is used to attach a beam or a shell. Now in this case, we use the word beam just to show that we are going to attach something that has 6 degrees of freedom, so displacement and rotation, to a solid which has only 3 degrees of freedom, so only the translation of degrees of freedom. So basically, this one can be used to attach a beam or a shell to the face of a solid. Now, second point, it is not an OpenC's built-in constraint. In fact, in OpenC's, you don't have something which is called beam to solid coupling. Instead, it is a STKO's automation. What does it mean, automation? It means that it's not something new. It's just a collection of OpenC's components that are put together so that the user can create this combination of constraints much easier. And in fact, the beam to solid coupling is nothing but a combination of equal DOFs and rigid links. So here is a small scheme. So imagine you have a beam and you have a solid. So imagine you're creating a simple model of a beam, and here you want a detailed model of the beam made with a solid, okay? And now you need to attach them. Now, as you know, in OpenC's, you cannot attach directly something that has 6 degrees of freedom to something that has 3 degrees of freedom. Well, first of all, because the rotation are not transmitted, but also because in OpenC's it is not simply allowed, okay? So what STKO does, just by creating a beam to solid coupling that attaches the master node of the beam to the slave nodes of the solid, behind the scenes, STKO will create some duplicate nodes with 6 degrees of freedom, which are these 6 auxiliary nodes. They will share the same position of the solid nodes. Now, in this drawing, I draw them with a fake offset here, but in reality, they will have the same position of the solid nodes. Now, this one will be attached, will be equipped with 6 degrees of freedom, and they will be attached to the beam using a rigid link. And then they will be attached to the solid with an equal DOF in only 3 degrees of freedom, okay? So basically, this is equivalent to attaching a beam directly to a solid in such a way that the rotation of the beam will affect the displacement of the solid, okay? So now going to the example, and this example is the one that you can find here, 02 beam to solid coupling, okay? Okay, so in this example, I'm going to create first the drawing for my beam. So if I remember, in the example, it was 2 by 2. Oops. Okay. Now we'll extrude this one of, let me go in orthogonal mode of 5 units. And then I can get rid of the bottom face. Then I want to draw the extra part, so the other 5 units of this beam using a beam element and not a solid element. So basically I simply draw an auxiliary line here just to have a point in the middle. Okay, so they can use the OSNA. Now I can get rid of this line. Okay, now I can extrude the vertex so that I can create a beam here of other 5 units. Okay, and I can get rid of the node. So basically now we have two detached geometry. So the bottom solid and the top beam. Okay. Now basically what I want to do is to make them simulate a beam of 10 units, but half of this beam will be modeled with a beam element. The other half will be modeled with a solid. And then I need some way to attach them. Okay. So before creating the attachments, let's go first to the property. And here I want to create a physical property for the concrete. Now in this case only elastic. So material, go to materials and D, Other ND material, elastic isotropic. Actually, this is not complete. I'm just using some fake units. So 1000, 0.2. Okay, and I can drag and drop it on the solid. And then I need an elastic section for the beam. Section, sections elastic. It will be 2D, the 3D, okay? So the section will be a cube, or box section, 2 by 2 units. Now, I don't care about the millimeters or meters here, I'm just working in units. So this is fine. 1000 here, and 416 the shear modulus. This is fine, I can drag and drop it onto the beam. Okay, so as you can see, basically they are the same, but one will be modeled with solid and the other with beam. Element properties, so I need two elements here, one for the solid, and I can choose, for example, the, what is it, brick elements, SSP brick, okay, and I select this one and I drag and drop the solid element. Then I create an elastic beam column element, model, beam column elements, elastic beam column, and I just need to in 3D. Okay, I select the beam and I drag and drop the beam element. Okay, let me save this file in the meantime. This one will be exe02. Oops. Beam solid. Okay, so we have the physical property, we have the element properties. I need to create an interaction for applying the loads. And I choose, as usual, a time series, a linear time series. Okay. Then I need an interaction, as I said. Okay, so I go back to geometry. And here, as you can see, one of the new features of STKO is that now you can decide if the display options should be automatic or not. Now, in the previous version of STKO, it is automatic. So whenever I switch from property to geometry, okay, the visualization changes. Otherwise, now you can choose to visualize everything at once. Okay, it is just an option. Now I need it to be automatic. Okay, so that it is easier for me to create the interaction here. So how do you create the beam to solid coupling? So first of all, what I want to do is to attach this node of the beam to the top face of the solid. So I go with interaction, add, and I call this one coupling. Node to node link as usual. Okay, so the master node will be, as I said here, the master node will be the beam. Okay, and the slave nodes will be those of the solid. So I select this one, right click, and then I go here, I click here, and of course here I have two options. Do I want to select the solid or the face of the solid? And in this case, I want to select the face. Okay, so right click, and as you can see here, all the slave nodes of the top face of the solids are connected with the beam. Okay, so of course this one is only the interaction. Now we need to go to the condition and to assign something to this interaction, as we did before. So the first condition that we create is a fixity for the bottom. So under model, constraints, single point, fix. We are in 3D. Only displacements because I'm constraining the bottom node, the bottom nodes of the solid, so I don't have any rotation here. So I select this face and press OK. Now, as you can see, for example, here I'm in geometry, but I cannot see the condition. I should go to condition to visualize them, right? In the new version of STKO, however, you can also choose not to use the automatic display options, so I can see everything at once. So I can see both the extrusion here of the property, but also the condition. Now in this case, I don't want it because for me it's much clearer to visualize them like this. So I go in condition tab. Okay, so we applied the fixed at the bottom. Now I want to apply a constraint for the coupling. Now let's first start with a wrong constraint. So I call it coupling. Let's first start with an equal DOF instead of a beam to solid coupling, and let's see what happens. So MP, and I simply use an equal DOF. Of course, I cannot use a rigid link because, as I said, the plain rigid link of OpenSys only works with master and slave nodes, which are both 6 degrees of freedom. But as you know, in this example, only the beam has 6 degrees of freedom, while the solid has 3 degrees of freedom. So I cannot use the rigid link. So someone else may think that I can use the equal DOF. But as you can see, with the equal DOF, we will not see any connection with the rotations, okay? So let's assume I can use an equal DOF. Oops. Okay. And I select this interaction here. That's okay. Okay, so we have the fixed at the bottom, we have the coupling here, and then I want to apply an applied rotation here at the top, okay? So I go here, and I choose load. So I go under loads, SP, prescribed value. So we are in 3D, displacement and rotations. And I want to fix the Y rotation to a certain value. Now in this case, once again, 0.5 radians. But I also want to fix at 0 the other two rotations, okay? So I click on them. So only the Y will go from 0 to 0.5. Oh, I think we have other people. Okay, from 0 to 0.5. And I want to apply this one on the top node of the beam, okay? Perfect. Now we can go on with the analysis steps. So once again, first of all, the recorder. And PCO recorder, and this one will be 02xn. And I want just to visualize displacement and rotations. Okay. Then I need to apply the boundary conditions. So I go to pattern, add pattern, constraint pattern. So we have one single point for the fixed at the base. And we have one multi-point constraint for the coupling. Okay, which, as I remind you, this one will be the wrong constraint, an equal DOF, and you will see why. Okay, once we have them, we need to apply the loads. Pattern, add pattern, load pattern, and we choose the linear time series. Then we go under single point constraints, and we add the load here. Fine, and now the analysis. Now here we are in a static. As I told you, we cannot use the plane constraint. Here the constraint can be quite complex, so I usually prefer to go with penalty. Now once again with penalty, as you can remember, we need to choose a significant value for the penalty here. I've already talked about this in the previous webinar. Now we have a Young modulus of 1000, so it's of the order of 3. We need to add 8, so 1 to the power of 11 is fine. Also because my mesh size is equal to 1, okay? So this one is fine. The problem is linear. And just 10 steps just to visualize the animation. So this is fine. So everything should be fine. We just need to mesh here. So mesh controls, I want to use solid elements which are hexahedral. So select this one, assign, done. And then I want to use a mesh size of, let's say 0.5. Okay, done. And build mesh. Okay. Now let's try to analyze this one, and you will see that here you don't have an actual continuity, okay? So let's analyze it. Okay. Post processor, open, and we go to XA number 2. Okay, so here is what I get. As you can see, the beam is bending, but the solid here is fixed. Why? Because we use an equal DOF. So the equal DOF is actually coupling only the displacement, but no rotation. Now here I applied a constant rotation. So the rotation goes here from the applied value to 0 and will not transmit anything to the bottom solid. So basically here, I've not connected anything. But what happens instead if I change the coupling from... Oh, and by the way, if I try to select a node here, like this one, you will see that it simply selects this node because there is no other node here. So that's fine, only one node. Because of course it is possible to connect with an equal DOF the beam with the solid without creating an extra node. Now you will see instead that when I change this one from equal DOF to beam to solid coupling, so I go to constraint, multi-point constraint, beam to solid coupling. Here you don't have any option. Okay, you just need to change it and run the analysis again. Okay, post processor, reload. Okay, now basically you can see that the solid is bending according to the beam. Now, in fact, the rotation of the beam has affected the displacement of the solid. Okay, now if I go here and switch off the extrusion of the beam, I can show you that basically, if I try to select one node here, STKO will ask for what of the two nodes you want to select, because there is node number 2, which was the original node in STKO. And then this other node here, which is the duplicated node with 6 degrees of freedom. So coming back to this drawing, this one was the original node. The second one is the auxiliary node, okay? So this is this is why we managed to connect beam to the solid, because there is this intermediate layer of auxiliary nodes. Okay, so this is pretty easy. Let's say, okay, this one is not important. Okay, so this one is an example of a kind of more involved constraint that we have in STKO. And as I told you, it is not a constraint which is available in OpenSys, but is actually a collection of other kind of components that instead are available in OpenSys. And when you put them together, you can obtain new elements. So this is one of the nice things of OpenSys, connected with a user interface such as STKO. You can use automations in such a way that your modeling is faster. Okay, so now going to the next example. The next example is a beam to solid bar slip. It's very similar to the beam to solid coupling. It's slightly more complicated because you have also a uniaxial material instead of only kinematic constraints. Now, since this one is going to take a little bit, probably I will talk about it as the last topic. So I will first go in this other example here. So let's take this one for the last, okay? So beam to solid bar slip is the most complex of them, so I will talk about it later. So what I've done up until now is equal DOF and ridge-link and their combination into what is called beam to solid coupling. Now, all of them are kinematic interactions. So no extra element, no physical property, no constitutive relation between them. But actually, you can use the interactions in STKO also to create physical connection, like interfaces of cohesive zones. Here I call them distributed springs because when you use the interaction with the zero length element, basically what you create are springs in OpenSys, zero length elements. But in STKO, you have the option to make them distributed in such a way that when you define them, you can define them not node by node, but surface by surface or edge by edge. And then STKO will do all its own calculation to compute the lumping factors for them, okay? So we'll show you a simple example of how to create a cohesive zone between two solids that finally can separate from each other, okay? And then I will go back to the beam to solid bar slip, which is actually a combination between a kinematic interaction and a physical interaction. Everything put into a single complex constraint. Okay, so let me start a new file here. basically what I'm going to create is what you can find in exe 0.4, and then I will go back to the bar slip. Now, just to show you what it is, you can see basically it is a two faces. Okay, let me go into these are 2D example. Here we have two faces. They are fixed on the right hand side here. The two faces are separated, but then there is an interaction between them. And this interaction has no condition, but it has a zero length element and a zero length material, which is actually a damage model with an exponential softening in tension. And then I will pull these two faces, one in the upward direction, the other in the downward direction, so that they will separate from each other. Okay. Here I will also show you how to create loads that are function of space and what else. Let me just see how much I have to displace them. 0.1. Okay. And let me remember just a little bit the property for the nonlinear material. It was 3 and 0.1. Okay. So let's start a new file, which is this one basically. Okay, so here I'm going to 10 units in the grid. Okay, so first of all, I want to create a face, which is 100 units here and 30 units in height. Okay, and then a copy of it. Okay, now as you can see, there are two separated faces, so they are not connected in any way. So create a simple linear time series for the application of the load. So time series linear. Then we need to create some physical properties. One will be an elastic concrete, because we will treat these two faces as elastic, and then the only nonlinearity will be here in the middle. Okay. So we want the material ND, other ND material, elastic isotropic, and it will be 30,000 and 0.2. Okay, and I select both faces and I simply drag and drop the concrete. And then I do the same for the element property. We go here and we choose a quad element. So we go under quad element. SSP quad. In this example, it will be a plane stress with a thickness of 1. So, okay, once again, I select both of them and I drag and drop the element. Okay, now we need to create the interaction between them, because in this way, or actually, let me do the analysis now without anything in between, and you will see what's going on. And then we will add a cohesive zone here in the middle. Perfect. So let's go to conditions. Fixity, constraint, SP, fix. We want to fix everything only in the right-hand side here. Okay, so let me go back to the conditions so you can see them. Perfect. So this one is fixed. And then we want to apply two loads here, one going upward and one going downward. Okay, so that these two bodies will get separated. And these two loads actually should be linear. So they should go, let me do a drawing here. They should go from a maximum of 1 megapascal here to 0 here, and then the opposite, okay? So -1 and +1, okay? And here I can show you how to do this kind of spatial dependent load in STKO. Okay. So it's quite easy. So remember that here the coordinate of x is 0 and it goes to 100, okay? So I go under load positive, and I go here, loads, force, edge force, because we are going to apply a distributed force on an edge. Now, by default, the mode is constant. So in our previous example, I've only shown how to apply constant forces, okay? But if you look here, you have another option, which is as a function, okay? So in this case, I can assign some values to the fx, fy, or fz as a function of space. Here there is an example, okay? So you can use any kind of Python language, okay? So in this case, I want to apply only a force in the y direction, which is equal to 1 at position 0 and 0 at position 100. So how can I do this? So first of all, I can write x minus 100, because here x is 0, here it is 100. So if I remove this 1, or actually it is 100 minus x, okay? So it goes from 100 to 0. Then I divide it by 100, so I normalize it. So it will be 1, okay? So if I click on this one and I press OK, you will see that I have a linear varying load that goes from 1 to 0. Then I do the same for the bottom with a change in sign. So I clone it, I can press edit. Actually, if you want to make it more involved, you can also do it with a single statement here using an if statement based on the y position, but I don't want to make it too complicated. So I simply go here, I put a minus here, and I select this one, and I select this one. Okay. Okay, so now as you can see here, I have downward pointing arrows, and here they are upward pointing. Okay, so I can go now in the analysis steps. We can create a recorder. Recorder and PCO recorder. And one will be 03xn. I need displacements, and I also want to visualize the stresses. Now, since it is an SSP, I need to write just the stress keyword here without the material point keyword. Okay, so this is fine. Then I need to apply boundary conditions. So add boundary conditions, model, pattern, add pattern, constraint pattern. And here we have only one single point constraint. So I fix it. Okay, now we can apply the loads. Pattern, add pattern, load pattern, linear time series, and the loads here this time are forces, so I apply them here. And load positive and load negative. Okay, so we have all the loads, and now we can go with the analysis. So we go under analysis command, static, plane constraint this time is fine because we are not applying any non-homogeneous constraint or non-identical constraint. The problem this time will, well, in this case is linear, but then when I will apply the nonlinear material, will not be linear. So let's keep it Newton. Then displacement increment test, this one is fine. Actually, let me go with the Krylov one. There we go, load control. We can do an adaptive time stepping if we are not sure about the convergence. 100 time steps as a starting point, and this is fine, okay? Okay, now if we want to visualize something, actually we can also use, or actually I don't want to do a load control. Actually, I would like to do a displacement control, because when I will apply nonlinear material here, I will have softening. So to do a displacement control, the first thing that I need is a selection set. So new selection set, and I select this node here, right click, and I call it control node. Okay, so I'm going to go to the analysis. I go down here and I choose not load control, but displacement control. Selection set will be the control node. The DOF that I want to control will be the displacement in Y, so DOF number 2. And the target displacement will be 0.1. Okay, perfect. So first I need to save it. This one will be actually 0.4 because the 0.3 will be the beam to solid bar sleeve. Okay, just let me change the name of the recorder because I called it 03, actually 04. Okay, so first I want to run this analysis, and you will see that I will just have a linear behavior. Now, before looking at it from the post-processor, I want to show you how to use the monitor so we can actually see the results in real time. So monitor, and I want to monitor, what is it? Miscellaneous command, monitor. And I want to create a graph where the x-axis will be a displacement. Will be the displacement in y direction of the control node, while in the y-axis I just need the pseudo time step will be the load multiplier. Okay, so here what I expect is a linear graph. So I go to mesh. Now the last thing that I need to do is to save it. Go to mesh control, phases, and I want to make them structure and quad. Sign, done. And then I want to use a global seed, uniform by size, equal to 1. Sorry, 10. Otherwise it's 2. Okay. And build mesh. Okay, now we are ready to run the analysis. Okay, so we got 7, perfect. So what I expect here is a linear relationship. Okay, of course I need a force. Okay, so it goes from 0 to 0.1 to a force of 0.6. Okay, perfect. Let me close it. And if you go to the post processor, of course I want to increase a little bit the displacement information. Let's go to the very end. Okay, so this is what happens. Okay, so let's do an animation. Okay, a simple bending of the two bodies. Of course, they are not connected between each other, so the relationship was linear. And as you can see here, there is nothing in between them. So let me switch off the grid. You can see there is no element connecting them. Of course, because we don't have any interface element. Now I can do the same using a nonlinear cohesive zone. So basically the two bodies will be attached up to a certain point, and then when this cohesive zone will break, they will separate, okay? And of course here we can also see just to show you that there is no cohesive zone, we can look at the stresses. If I look at the maximum stress, it will always be on the bottom line like this. As you can see, the stresses are fixed. Why? Because there is not an opening crack. The two are already open. So the maximum stress, as you can see, it will be here in the most bent zone. Okay. So as you can see, there is no change in the stress distribution. It is fixed at that point. It is all increasing in value. And this makes sense because the crack is already open. There is nothing that was before connecting them and then was open into a crack. Now we do the opposite instead. We create an interaction between them, simulating an initial connection. I can call it interface. Okay. And I want to use the bottom line. So geometry edge, geometry 2. Actually, no, let me see what is the bottom geometry. So sometimes it's useful to rename them. So this one, geometry 1, will be the bottom one. Why it's useful to rename them? Because when you have that overlapping selection, you can see the name of the geometry. It's one of the top. Okay, so when I create an interaction here, okay, and I call it interface. And I don't want to select faces, okay? So I click here, I have two edges, oops, here. And I want to select the bottom line as the master, then right click, and then I can simply select the other one as slave, okay? And as you can see, I created an interaction between them. Perfect. Now this interaction doesn't have anything, so I need to create a material model for it. So I first create a traction separation law. Now, for the sake of simplicity, I can use any kind of uniaxial material that I want. Now, in my case, I'm going to use the damage TC1D. It was concrete, so I use the same elastic properties as for the concrete. Here I use 3 and 0.1 of fracture energy. Now keep in mind that here they should not be, the abscissa should not be the strain, but actually it is the displacement jump. In compression, I don't need anything, I just put some values, but they don't go in compression. Okay, so I simply don't need anything here. Also here, I want to use the implex, so I will not have convergence problem here. If I do a simple test, monotonic test in tension, okay, so this one will be the behavior that I will assign to this traction separation law. Perfect, so this one will be a uniaxial material. So as you remember, when I want to create springs, I need to create a zero length material. So zero length material, I go in model, special purpose, zero length material. Once again, I have a mouse lag here. Zero length material. We are in 2D, only displacement. I don't want anything in X. I just want something in Y. And I want to use a traction separation law in Y. Okay, so perfect. And then I can select the interface and I drag and drop the zero length material. Then of course I need to create a zero length element. So I go under model, zero length elements, zero length, 2D. And then here it is what I was referring to when I talked about distributed springs. Now, as you know, in OpenSeas, a zero length is actually a concentrated spring, okay? So whenever you create a zero length element, it connects a node to another node, and it wants a force versus displacement relationship, okay? Now, the problem is that it is fine as far as you are connecting point-to-point connections, but in this case, it is an edge-to-edge, so it is distributed. So if you want to do this one directly in OpenSeas, you need to know the size of your mesh, and you need to say, okay, I want a traction separation law, which is based on stress, and then I multiply this stress by the tributary area of my model. Now, this one is quite tedious because sometimes you don't have a regular mesh, or sometimes you want to refine your mesh. So every time you refine your mesh, you need to change that value. Now, STKO has an option here. Whenever you create a zero length element, you have an option called distributed. So if you check on this, STKO will basically take the constitutive model that you gave to the zero length, and it will multiply it, but actually multiply, it will use a series material that will multiply the output of that material, of that uniaxial material, with the tributary area, or in this case, the tributary length of the element where this law is connected, okay? So basically, you just need to remember that if you click on distributed, you can assign values per unit length or per unit area, as I did here. Okay, so this is what we want to do. And I will demonstrate you that this one allows you to refine the mesh having the same results. Okay, so you don't have to go and change the results of the traction separation here. So I press OK, and I select the interaction, and I drag and drop the element. Okay, so now they will be part of OpenSeas. Okay, so we can simply run the analysis now, and what I expect is not a linear behavior as before, but what I expect is something like, if before we were having a linear behavior like this, now I expect something which is like this, then softening, then goes back to hardening. Okay, basically with the linear behavior given by this constraint. Okay, we have the mesh. Oh, no, we need to remesh it because, of course, we changed the geometry. So now, as you can see, it first goes to a certain value and then goes up following the linear relationship of this one. So now let's try to see what's going on in the post-processor. Now, as you can see here in the previous example, I've shown you that there is no change in the distribution of stress. Now, in this case, instead, I should be able to see the stress tip going from this point to this point here. So if I reload it and I try to move it, you will see now, actually here it is not quite visible because the mesh is very coarse, but then I will refine the mesh and you will see it. But basically you have a stress tip here that whenever it breaks, and as you can see now here you have elements, because they are the zero length elements for the connection. Whenever they break, the two elements will separate and the stress here will jump down to zero. Let me move this one. Up to a certain point when they are completely separated, and so the stresses will remain fixed at their original position, okay? So this happens only when they are completely separated. Now I do the same, refining my mesh, and you will see that the result will be the same. So just to remember the result, oops. It goes to 6. Yes, then it goes down and then up again, okay? Now let's see, if I don't change anything to my material, just because I use the distributed, when I go to mesh and I change the mesh size, for example, uniform by size, before it was 1, now 0.5. Not 0.5, sorry, it is too fine, it was simply 5. And run the analysis. Okay, as you can see, the response is the same. It's smoother because, of course, now you have more elements. Okay, so the more elements you have, the smoother it is the output, but it is the same. It is not changing. And let's see how the stress tip is evolving. Now it will be more visible. Now, as you can see here, it's kind of more visible, the stress tip going there. And then when it is completely broken, you see only the stresses at the bottom phases, okay? Then let's give it a final remeshing so that we can see it even more clear. It was 5, so 2.5 now. Okay, should be fine enough now. And once again, I expect the results not to change, just to be smoother. Okay, and in fact it is. I can switch it off, reload the output. Oops. And do the animation again. Oh yeah, the stress tip is clearly more visible. Okay, so this one is an example of how to use the STKO interactions to create physical constraints, not kinematic constraints, okay? And this one was the last topic. Now I go to the real last topic, which is the beam to solid bar slip. Now in this case, I'm going to show you a quite complex model, which is a three-dimensional model of the bottom of a column, where it is modeled in 3D with physical rebars, and there is also the rebar hole, and the rebars are connected to the solid, with a particular constraint, which is in fact this beam to solid bar slip. Now it will take a while to create this model. So probably what I will do, I will show you the model, how it is. Then I will give you some tips on how to do this solid modeling. And then I will start with the model already done, because otherwise it will take too much time, so that we have some minutes for questions. So this one, I decided to keep this one for the last, because it is actually not completely a kinematic interaction. It's something in between, because the beam to solid coupling, and now I go here, is very similar to the beam to solid, the beam to solid bar slip is very similar to the beam to solid coupling, in the sense that it is used to attach a beam to the face of a solid. Now in our case, it will attach the rebar to the internal face of the rebar hole. Once again, it is not an OpenSys built-in constraint. It is actually an STKO's automation. And once again, it is a combination of something that is already available in OpenSys. More specifically, it is a combination of equal doves, rigid links, as in the previous case, plus a uniaxial material. Why? So basically here we have the beam, which represent the rebars. Then we have this space here, which is the hole of the rebar, and then we have the solid body. Okay. So as you know, the solid bodies has nodes with 3 degrees of freedom. The beams has nodes with 6 degrees of freedom. The beams will be the master, and the solid will be the slave. So once again, we cannot attach directly a beam to a solid. First, because they don't have the same degree of freedom, but also because we want to add a uniaxial material for the bar sleeve. So actually, what STKO does in this case is to duplicate the nodes of the solid with these auxiliary nodes of 6 degrees of freedom. As I said, they will be placed at the same position of the solid. Now, for the sake of the representation here, I gave a gap. So now the beam and these auxiliary nodes will be connected using rigid links, okay? So that the rotation of the beam will affect the displacement of these nodes, which are at a finite distance. While the auxiliary nodes will be connected to the three DOF nodes of the solids with an equal DOF in the Y and Z direction. Actually, this one is in the local coordinate system, okay? While in the axial direction of the beam, instead of using an equal DOF in that direction, it will use a physical material. That's why it is a combination of a kinematic constraint and a physical interaction, okay? So why do we use a uniaxial law here in the axial direction of the beam? Because here you can simulate not a perfect bond, but the typical bar sleeve behavior, okay, if you want. Actually, it can be used for many other purposes, but in this case, I will use it for modeling bar sleeve. Okay, so let's go back here. As I said, it will take probably too much time now to do the entire model. So I will show you the model, how it is. I will give you some tips and tricks on how to create that model. So let me save this one. And I'm going to open the... Oh, by the way, here you will see 2 folders with the 03 number here, the beam to solid bar sleeve, the first one and the second one. Now, actually, the first one is the initial model without using the bar sleeve. It's only using the beam to solid coupling, so a perfect bond between the rebars and the solid. And then I took the same and I simply changed the constraint to include the bar sleeve behavior, okay? So let's start with the first one. So when you open this one, you will find a solid model. Let me go back to geometry, so I will explain you how it is made. Okay, so first of all, I have a column down here. Okay, so the bottom line of a column, the foot of a column, then a piece of a column. Then here I have a constraint that simulates that the column face remains planar. Then I will show you how it works. So the first geometry will be a column. Then if I switch it off, which is this one basically. If I switch it off, you will see that here you have the rebars geometry. Let me select them. Okay, they are simple lines, actually wires. So straight lines connected with a arch here. Okay, and we have 6 of them. Now I simply put them together with a compound just because it is easier to select a group of lines rather than 6 lines. Then finally I have a control node here. This control node is actually a 6 degree of freedom node, which is connected to the top face of the beam using a beam to solid coupling, so that I can take that node, apply a rotation, and the entire face of the solid will rotate, okay? So sometimes the beam to solid coupling is also useful to apply rotation to the top of walls or solids, like in this case, okay? So show all. Now, just to show you how you can do this kind of model, I will just give you some tips on how to do this solid modeling. Actually, I will show you only a piece of them. So how to extrude a solid like this one, how to create the rebar, how to create a hole, okay? And then, of course, I will start with this model, otherwise it will take too much time. So let me start with a new file. Okay, let's say now in that example, I had a rebar, sorry, this one is time cut, perfect. So the bottom of the footing was 400 times 400. So it was like this. And then in the middle, I have, actually it was 30 by 30. Don't remember, well, actually it's the same now. It is just how to show you how to model this one, then I will open the other one. Now let's assume here I have my column, which is 200 times 200. Okay. Perfect. So the first thing that I did was to extrude with the orthogonal constraint. Actually, before extruding, I need to create planar faces from the outer line. So click on this, right click, and then I can get rid of the outer line. And now I can extrude the bottom face in the upward direction using the orthogonal constraint of a certain amount. I think it was 300 probably. Okay. Okay, and then I can get rid of the bottom face. Okay. Now I can select this one, this line here, select. I go in the front view, oops, front view here, and then I can move it up here. So I can start the extrusion from here. So once again, I want to convert this one into a face. So I click on planar faces command. I select this one, right click, and I get rid of the outer wire so that I have this face here. I select it and I click on extrude once again. And here you can choose the extrusion either by here or typing the dimension down here. So 400, for example. And then I can get rid of the face. Okay, so now we have two solids. Now I want to join them. So I can either use the merge command, but actually in this case, I'm going to use a non-structured mesh, so I can just use an union. Okay, so I can select both of them, right click. The union will just create one single solid. Of course, this one cannot be meshed as a structured mesh. I need to use an unstructured mesh. Okay, so let's say this one is the model of your column. Now you want to create the rebars, okay? So let's go to the front view first. And I want to switch off the faces so I can draw directly here. And let's see how you can draw a line which is connected backward down here. So let's say I want to start from here, and then I go down here, up to here, for example. Okay, and then I want to create a circular connection. So I can go here, arch of ellipse, or actually even a circle. Or you can create a circle and then remove the places, or an arch of ellipse. So I click here on the center, specify the ellipse center, specify the first and the second. Actually, here I need to remove where is it? The orthogonal constraint. Okay. So I want to go down here, and then the thickness here. And then here I can specify the direction. Actually, if you want to invert the direction, you can press Ctrl, so it will go on the other side, okay? Up to here. Perfect. So now I can join them using the merge command, okay? And once I merge them, I can go into sub-selection and remove these two pieces. Okay, so what I have now is a wire that is basically my entire rebar here. Okay. So perfect, now I have the solid and the rebar. Now what I need to do is to create a solid for creating the whole of the rebar, okay? So what I need to do first is to create a circular line from here. And it should be, let's say the radius was 8 because I was creating a 16 millimeters, a bar with a 16 millimeters diameter. So, okay. So this one is my rebar section. Then I can convert it to a planar face. So I select it, right click, and I get rid of the outer line. And then I want to extrude this one following a path. Okay, like this. So instead of using the extrusion, I can use the sweep command. Okay, so sweep, select the profile shape. Now the profile shape will actually be my cross section. So this one, right click, and then select the spine. That will be this one. Okay, if I select the spine here, you will see that the extrusion goes down here and then evolves along the direction of the line, okay? So basically now I have one solid here, which is my entire, then I have this face here, which is not needed, so I select it and I remove it. So I have this one, which is the rebar, and this one, which is the hole of the rebar. So I can use this one to create a hole here. So how can I do it? So I can go here now. I can move it, and I can place it at its position, let's say here, okay? Now I can copy, paste them all around to create duplicates of them. Now I don't need it. And then once I have all these solids for creating the holes, I can simply go on subtract and I select the first solid, right click, and then the solid that I want to use to create the hole, which is this other one. Select and right click. So basically this one will create a hole inside here, and there will be the beam inside, okay? So basically this one is the procedure that I used to create all these holes inside my solid, okay? Now for the sake of the simplicity, I will start with the ready-made file. I will just explain you how they work. So beam to solid bar slip, which is this one. As I said, I created this entire model. So I have my column, I have all my rebars, I have all the hole done here. Then I created a control node that will be attached later on. I will show you how. Then I have two interactions. One is the coupling. If I select them and I switch off the faces so you can see them, it is basically an interaction that I will use for the beam to solid bar slip, where the master are the rebars and the slaves are the faces of the hole. Okay, so that basically it will create a connection between every point of the rebar and the normal point on the surface of the holes. Okay, then I have another interaction here at the top. Not I actually select, which is this one that basically connects the control node to the top face of the beam in such a way that I can apply a rotation at this node and the entire solid will bend, okay, according to that rotation. So finally, I have physical property for the concrete. Once again, here I'm using the DAM-HTC 3D. I've already explained this material model in other webinars. Then we have a uniaxial material for steel, okay, because the rebars in our case are going to be modeled with fiber cross sections. So I'm going to use a fiber cross section for the rebars, which is pretty simple here. Just a circular cross section, few fibers. I don't need a lot of them. I just need them to create the nonlinear behavior of my rebars. And of course, I have the rebar property, which is a Lobato integration scheme. I just need the minimum of 3 integration points because, by the way, this one will be meshed, so I don't need many integration points there. Then as regarding the finite element, I decided to use a tetrahedron for the solid model, because as you will see in my mesh here, this mesh cannot be meshed with a structured mesh. So I can only use tetrahedron in such a way that I can also do a refinement here. And of course, I can choose the tetrahedron element in OpenSys. Then for the beams, I use the displacement beam column. And then we go to the condition. So the first condition will be a fixity at the bottom. Okay, so all the bottom face is fixed in all degree of freedom. Let's go to the condition tab. Then we have a coupling here, which in this first example is a simple beam to solid coupling. So there is no slip. Why? I decided to create two models so in such a way that you can compare them, okay? So if you run the first model, you will see a perfect bond and you will see the behavior. Then in the other model, this one will be simply changed to a beam to solid bar slip. Then the top interaction, of course, will be a simple beam to solid coupling. As I said, just because we want to rotate them. That's fine. And then we have an applied moment at the top node. As I said, this is the reason why we decided to create this interaction in such a way that we can apply a moment instead of a distributed force. Okay? And then this moment will be controlled in displacement control. So here we have the recorder, then we have the boundary conditions. And for the boundary condition, as I said, we have a fixity here at the bottom, and then we have two multi-point constraints. The top coupling and the coupling between the rebars and the solid. Then we apply the load with a linear time series. Then here we have a monitor because we want to monitor what's going on about the rotation, about the y-axis of the control node against the pseudo time step, because the pseudo time step in a displacement controlled analysis is the load multiplier. So then we go to the analysis. In this case, the mesh is quite large, so we need to go with parallel analysis. So I decided to use the penalty method. Here I have a parallel number, the MUMS solver, which works for parallel analysis, then the Krylov-Newton, node displacement increment test, because I'm using penalty. And then since I want to do parallel displacement control, I need to choose the parallel displacement control because I'm doing a parallel analysis. So I choose the selection set for the control node, and the degree of freedom will be the fifth one because it is the rotation above the y-axis. And the target displacement, which in this case is the target rotation, will be 0.005 radians. Then I use an adaptive time step starting with 250 steps. And then if I have convergence problems, it will try to reduce this time step. So, okay, now, of course, I don't run the analysis because it will take about 15 minutes with 6 processors. Oh, by the way, in my case, I decided to use, 6 processors. So I go to the partition, I choose the number of processors that I have, and then I click on partition. Actually, I have 8 processors. I decided to use 6. Don't use all of them, otherwise your computer will be all busy trying to solve OpenSys. So keep a couple of cores free for your other tasks. So in my case, I have 8 cores. I decided to use only 6. And then, of course, when you run the analysis, you should switch to OpenSys MP. Okay. Now, once you run this analysis, this is the output that you will see. This is the 0.3 beam to solid coupling. Okay, so this is my entire mesh. Now, as you can see here, just from a first visualization of the displacement, you will see that I have multiple cracks here and a final huge crack here at the bottom. Why? Because I have a perfect bond between concrete and rebars, and you will see a lot of cracks down here. And then you will see instead the behavior using the bar slip. Now, to create a nice plot when you have this kind of solids, you can do something like, first of all, I want to switch off the mesh edges. I don't want to see them. Then I want to visualize move this one. I want to visualize the damage. This is actually the last step. So here we'll have a lot of damage. Then I want to go to the top and I want to see what's going on inside. So I can select more or less roughly half of it, and then I can switch it off in such a way that I will be able to see what's going on inside the rebars here. So I switch it off. Okay. So this one is the inside of my column. I change it to hot, so it's nicer to visualize the development of the cracks. And then I can also switch off feature edges, okay? So I don't see them. And let's say I want to superimpose, for example, here I don't want to see the beam exclusions, okay? While the beams, I'm going to visualize them using the fiber color map. Okay, so I go here and I choose beam shell fiber color map, superimpose to this one. Now in the fiber color map, I want to switch off the feature and mesh edges so that I only see fibers. And in this case, yes, I can use this one. I want to visualize the strains. So basically here, we're going to see that the strains in the rebars will concentrate every time a crack appears, of course, because there is a plastification of the rebars in that point. Okay, now let's see, let's put a deformation of 100. This is the real end of the analysis. Now, in this case, it will be completely broken, and also 100 here. And then we will synchronize it using the video here. Okay, so starting from the beginning, this one is the behavior at the very beginning. Then let's try to, so here I don't have any damage. Then as I go further, you will see the first development of the first crack here, the concentration of deformation in the rebars. I can go on. You will see step by step that many cracks will form. Now another one in the middle. Okay, and then finally, since the rebars are strongly attached to the concrete, finally it will break the concrete down here, because actually I did this model very fast, so I created this connection very close to the bottom, and so a crack will appear down here. But all of this happens because there is a perfect bond between the rebars and the concrete. Okay. Okay, so this is the final behavior. So everything is broken down here. Now, basically, if I simply go in the preprocessor and change a couple of things, and you will see those changes here. I simply can open the other one. So if you open the 03 beam to solid bar slip number 2, you will see the same exact model, but there will be a difference. The coupling here now is not a beam to solid coupling anymore, but it is a beam to bar slip. So actually here I have just two values. The first one is the material tag, which is a uniaxial material that will be used in the local rebar direction to simulate the bar slip. Okay. So now in my case, I've chosen a 3-linear material, I think, because I was following the FIP model code. Okay, so given the concrete strength, I computed the maximum bond stress, and I simply use this kind of law. Of course, you can use more involved laws involving, for example, softening, but in my case, I use a simple hardening at the beginning and then perfect plasticity. And I used it in a simple fashion using a multilinear material, okay, like this one. And of course, otherwise you can use other materials, so you can use more refined points. See here, I just gave a few points, but it's enough for the sake of this explanation. So I first create the uniaxial material for the bar slip. Then when I am here in the beam to solid bar slip, I simply select that uniaxial material. And then I have a key penalty. So what's the problem with this key penalty? As I said here, the beam to solid bar slip as the beam to solid coupling, it is a kinematic constraint. But now there is a problem. As I told you here, the equal DOF will constrain only the Y and Z degree of freedom, while the X will be free and will use the uniaxial material. Now the problem is that this 3 degree of freedom will be should be defined in the local direction of the rebar. But with the kinematic constraints in OpenSys, there is a problem. They only work in global coordinate system. They do not work in local coordinate system. So basically, whenever STKO finds that this connection is given to something which is aligned with the global coordinate system, it uses the equal DOF. Otherwise, it uses a penalty factor. So this penalty factor, once again, should be large enough, but not so large, okay? So basically, this one will be used only in the curved areas down here. Perfect. Now, all the others are the same. Now, the only thing that I added here is an extra constraint, because here we have the top coupling, which is a beam to solid coupling that connects the center node to, let me go here, to the entire top face, okay? But then, since now I have a bar slip here, it may happen that this rebar can slip downwards. But here I want to simulate that this rebar here is actually attached to a plate that is used for bending. So basically, I created another interaction that connects the center to every top rebar. And this one, once again, we have a rigid link, okay? Why I didn't put these nodes inside the beam to solid coupling? Because the beam to solid coupling assumes that the beam here is 6 degrees of freedom, and all the slave nodes are 3 degrees of freedom. So I cannot put these ones as slave nodes because they are top of beam elements. So in this case, I simply need to create another interaction using a plain rigid link that connects 6 DOF of the master node to the 6 DOFs of the slave nodes. So this one is the only difference that I put together with the changing the solid coupling to the solid bar slip. So once again, I try to run the analysis. When you run the analysis of this one, you will see a couple of differences from this. Instead of visualizing all those cracks, you will see just this crack down here. That will be the only crack basically, because then the rebar will kind of slip and will not take with himself all the bottom line of my column. So let me open the output from the other file, which is 03 bar sleep number 2. Okay, so here I'm going to do the same. As you can see now, just from the displacement, you will see that at the end, this top beam is rotating along without breaking the bottom here. So once again, let me do the first step I did before. So I switch off the mesh edges, I switch off the feature edges, I visualize the damage. As you can see, the damage is very localized now in this fracture here. I go on the top view, I select half of it and I hide it. And I switch the color to hot. Okay. So now you can see that the cracks is very localized here. Even if I use the deformation output to 100 at the end, you will see that it is completely broken here. And here there is the slip. And then I will show you how to visualize the slip as well. Now here I want to switch off the beam extrusion because I will do the same as I did before. So shell fiber color map. Here I want to switch off the feature edges and mesh edges. And I want to visualize the strains, that's fine. And 100 also here. Okay. That's perfect. And let me create another plot now because we also want to visualize the bar slip. So we want to see what are the zero length elements that are most deforming. Here you see them actually as lines, but I want to visualize them using Gauss plot. So also here you can clearly see that the rebar is moving and is leaping from its original position, okay? Just by looking at the zero length elements. But if you want to visualize the result, you can go in Gauss plot. Now in this Gauss plot, I want to remove mesh edges and feature edges. Now by default, it is visualizing the damage, okay? So I can see the damage as Gauss points. But if I move it to the strain number 2 here, will be the strain of the zero length elements. I think should be this one. Let me see. And scale factor of 5, so I can visualize them. No, it is not that. No, it is not this one. It is, sorry, strain lines. This one, yes. Okay, let me remove it a little bit. Reduce it. Okay. And I want to switch off all this part of the model which is not necessary. So it's confusing. Okay. So basically now, let me go back to the, also here in the same deformation. Then let me go back to the end, and finally I will do an animation. But I want to show you how you can see the results of them. As you can see now, here I see a lot of Gauss plots, and those blue and red are actually showing the maximum deformation in these zero lengths, which is the maximum slip. And as you can see, it is concentrated around basically the cracks here, then it goes almost to 0 inside, and then also here, which is basically where the most, the majority of slip, of course. And let's try to see an animation of this. Of course, when the model is so huge, the animation will not be fluid, but of course you can create a render and then visualize the animation. Now we can go step by step. Here at the beginning should be the initiation of the crack. And the crack will slightly propagate there. And then due to the fact that the beams can actually slip there, as you can see, the slipping is increasing in that point, the crack will easily localize here instead of spreading all around as in the previous model. Now in my case, I used a very weak bond. Probably you can use a better bond and you will see more propagation of cracks. But this is just an example on how to use the bar slip. As you can see, the beam is actually slipping from its initial position. See? Okay. So basically, also this one is an example of interaction. It's probably more complex and more involved than the others. but it's useful to understand all the capabilities that you have with OpenSys when you use it through a user interface such as STKO. Because actually doing all this stuff manually in OpenSys, of course, is very complicated. So having a tool that helps you to do all of this is pretty nice. Okay, so I think we are done with today's webinar, and then we have some, let's say, 15 minutes for questions. So let me just come back to the Zoom here. And please, if you have any question, let me stop the sharing. Okay, so of course, thank you everyone for taking part of this webinar. And if you need any clarification, if there is something not clear about the constraints, we have, let's say, 15 minutes for questions. Okay, here is the first one. Can we use physical interaction for modeling cyclic behavior of interface elements in masonry wall in which brick separates? Can we use this physical interaction for solid 3D elements? Of course you can. Now I did it for the 2D case, okay? But of course you can do also for the 3D. You just need to switch on the distributed option, and the distributed option will automatically multiply the material that you give to the zero length with an area if you are modeling a 3D, or with a length if you're modeling in 2D. So they are the tributary length or tributary area. Okay, so of course it is possible. You just need a good 1D. Oh, but actually, the way I explained you, so using the zero length, is fine as far as the normal and tangential direction are uncoupled. Because if you use uniaxial material coming from OpenSys, and if you choose them, one for the normal traction separation law and one for the friction, they will be uncoupled. But otherwise, in OpenSys, you have other tools that can be used for coupling, like, for example, the contact elements. But of course, the same thing that I've done with the fourth example, so the example on physical interaction, can be done, of course, also for solids. So yes. And anyway, if you're interested in masonry, I don't know if you have seen our previous webinars, but we gave some webinars on micro modeling of masonry using all continuum elements. Now, in that case, for example, you can mix the kind of approach that we gave using also this approach to create a more detailed micro modeling. So you can have a look at the previous webinars and you can try to mix it with this kind of physical interaction. Third question, can you demonstrate a model of a catenary cable supported by 2 electric transmission poles under seismic time history motion? Actually, we can, but not now, because actually we have only 5 minutes now. But if you want, actually, we can use this one as a topic for a next webinar. So we can of course take it. In OpenSys, you have just one element that can be used for catenary cable. There is only one. So of course we can try to prepare an example like this for a future webinar. Let's say if you go on our forum and you post this question there, then we can use the outputs of that post to create a new webinar about this one. Okay. I just don't want to do it now because it is not related to the topic of this webinar, but of course it can be done. Okay, so if there is no other question, of course, if something is not clear, you can always use our forum. Yeah, there is another question. Thanks. That will be great, by the way. Is the demo version from your website a full version for a trial period? Yes, it is a full version, so there is no limitation for a trial period of 30 days. So yes, it is a full version. There is no limitation on the number of nodes, elements, or sequential parallel analysis. You can do whatever you want. Okay, I think we are done. So if there is no any other question, thank you everyone for taking part to this webinar. Yes, a full version. So thank you everyone for taking part in this webinar. And as usual, we will provide the video recordings and the contents file either tomorrow or in a couple of days, just the time to collect all the recordings. And you will find them on our YouTube channel and our website. And of course, if you have troubles trying to replicate these examples, because I understand they are quite complex, at least not the first ones, but the last ones on bar sleep, they are quite complex. If you have doubts, you can always use our forum. Okay. So thank you, everyone, and see you in the next webinar.